Hello, this is checkpoint 4.43. In this checkpoint, we're asked to find the limit as x approaches 0 from the positive side of x to the x. And if we just simply put 0 in, we get 0 to the 0. We kind of remember that anything to the 0 power is 1, but 0 to any power should be 0. So 0 to the 0 seems like it's one of those things that could be indeterminate. So this is an indeterminate form. This is one of 3 indeterminate forms of the form of a power exponent. So we're going to, whenever we have a power exponent indeterminate form, we would like to take the ln of something. And so for me, I'd like to let L equal to this limit itself. Limit as x approaches 0 of x to the x. And we would want to take the ln of both sides. So if we take the ln of both sides, we have ln of L is equal to the ln of the limit as x approaches 0 of x to the x. But because the ln is a nice continuous, strictly increasing one-to-one function and all that, we can put that inside of the limit. So we have limit as x approaches 0 from the positive side of the ln of x to the x power. Now, we take advantage of the properties of the ln. So we're going to take the limit as x approaches 0 of the x in front. So it becomes a power, or the power comes down as a coefficient. And then we have ln of x. Now, if we take the limit as x goes to 0 here, this will become 0. And ln of 0 will actually go down to negative infinity. So this is a 0 times infinity sort of indeterminate form. So we're going to want to use L'Hopital's rule here. But we can't use L'Hopital's rule just yet because we need to rewrite it first as a fraction. And we'll try to do that. Let x go to 0 from the positive side, and let's bring this x down in the denominator. So the ln x will stay in the numerator. The x will be coming down in the denominator as the reciprocal. So imagine this is to the positive 1. It goes down to the negative 1. So we'll say x to the negative first power, or you can just say 1 over x. Now if we send this off to 0, ln of 0 again will be infinity, or negative infinity. And then this goes to 0, this will become positive infinity because it's 1 over 0. So now we have a form that we can use, where we can use L'Hopital's. So we'll keep the equal sign going, but this time we'll put LH to say it's a conditional equality, and provided that our limits are going to exist, then this would be a true equality. Otherwise, it might not be equal after all. So we'll take the limit as x goes off to 0, and we'll take the derivative of each of the numerator and the denominator. So this is 1 over x. The derivative of the ln is 1 over x. This is negative 1 times x to the negative 2. Let us rewrite that. Not doing L'Hopital's rule again, but just simplifying. We'll take the limit as x goes to 0, positive side, and we will have 1 over x in the numerator, and we have negative 1 over x squared in the denominator. Let's do one more simplification. And we will have the reciprocal, so that'll be x squared over x. So this is just going to be x, or limit as x approaches 0. Limit as x approaches 0 of x, which is going to be 0. Now remember that this is not your final solution because the whole thing started with the ln of L equal to this limit, and we found this limit to exist, and so this conditional L'Hopital's equality means it's actually true. And so let's write it up here. Our conclusion we have ln of L is equal to 0, so we'll take the e of both sides. So this is going to give us L is equal to e to the 0, which is equal to 1. Okay, so this is our final answer, and our limit is equal to, so this whole thing will eventually equal to 1. Okay, another thing you could do, you should graph it using Desmos, type x to the x, and then see what happens as it gets closer to 0, and then you'll see that it should be equal to 1. All right, I hope that helps.